A DSLR is a digital single-lens reflex camera. DSLRs are successors to traditional film SLR cameras because they combine the old technology with the new digital technology. DSLRs use this digital technology to create and expose photos, which I'll talk more about in a minute. They typically have many buttons or wheels that are ergonomically placed for their functions, such as a shutter release button, which is used to actually take a picture, or in some cases adjust the autofocus and hope that it works. DSLRs are extremely versatile cameras as they are used throughout all different fields of photography and videography. They are used by sports photographers, landscape photographers, real estate photographers, etc. DSLRs are so adaptable to any situation because they have the ability to change and swap out different types of lenses. For example, a very wide lens might be used to show all the features of a certain room to sell a house, but a telephoto lens might be used to zoom in on some wildlife far away on an expedition. These cameras also have what's called a hot shoe, which is a place to mount various pieces of equipment for shooting photos and videos. DSLRs have the ability to adjust aperture, which is how open or closed your lens is, shutter speed, or how long the sensor is exposed to the image, and ISO, which is how sensitive the camera's sensor is to light. These three elements can be used with what's called the exposure triangle to properly expose an image. Most DSLRs have the ability to shoot in the RAW file format, which retains much more image data than JPEGs or PNGs, making editing a much simpler process later on because there's more room for potential. Despite the positives, DSLRs do have a couple setbacks. For one, there are a million buttons and features all over the camera, so learning how to use them can be pretty daunting. Also, the mirrors inside the camera can alter your perception of the image through the viewfinder. You may not realize it, but your focus could be slightly off, despite the clear image you see when taking the picture. First, you need a light source. Photons of light travel from the light source and enter the camera's lens. There are many types of lenses, but the basic idea is that the light goes through the various levels of optics and actually flips upside down. The light continues and eventually hits the reflex mirror positioned at a 45-degree angle. The particles then move upward until they reach a condenser lens and a pentaprism. The condenser lens adjusts the size of the image that the viewfinder will receive, and the pentaprism deflects the light in a way that flips it back right side up to be seen in the viewfinder. Once the photographer is ready to take their photo, they press the shutter release button. The reflex mirror is moved out of the way and the shutter opens. Light goes straight from the lens onto the image sensor. When the light hits the sensor, it's transferred into an electrical signal. The sensor actually measures the brightness and color of each pixel's worth of light and records the information. Then it's sent to whatever storage device is hooked up to the camera, which is usually an SD card, which can be removed and put in a computer to see the photo. DSLRs typically have either a full-frame sensor or an APS-C sensor. The APS-C is usually found in lower-end cameras and has a cropped field of view. Full-frame cameras capture more of an image, but they're more expensive. When using manual focus on your DSLR, it can be hard to determine whether subjects are in focus or not just by looking at a tiny screen. A cool way to find your focus is actually calculating it. This can be done using this formula, where f equals the focal length of your lens, do equals the object's distance from the camera, and di equals the image distance, or how far you need to adjust your lens for proper focus. For example, if you have a 10mm lens and a subject that is 1000 millimeters away, it can be found that you would need to adjust your lens by 10mm to focus on your subject. For my experiment, I took a series of photos of a lamp to show the extremes of the exposure triangle. I used a cheap tripod, a Nikon D3500, and a standard 18 to 55mm f3.5 to 5.6 lens. My first photo was my control. It was shot with an ISO of 100, an aperture of f3.5, and a shutter speed of 1/250th of a second. Using Lightroom, I generated a histogram to visually show my data with a graph. On the x-axis is luminosity, or the brightness of the image. The left is very dark and the right is very bright. The y-axis shows the frequency of the luminosity at those gradients. For this experiment, my independent variables were my aperture, shutter speed, and ISO. My dependent variables were the image's luminosities and luminosity frequencies. So for this picture, you can see that the darker parts of the image are very underexposed and the brightest parts are a little overexposed. During my first trial, I adjusted aperture. All settings remain the same as a constant except for the aperture. This photo was taken with an aperture of f5.6, and you can really see just how much darker the dark parts of the image became. The bright parts also got a little darker, revealing more detail in the highlights. For my second trial, I adjusted shutter speed. This photo was taken with a shutter speed of 1 second. Nearly all of the photo is blown out and is too bright, as seen on the right side of the histogram. This next photo was shot at 1/4000th of a second. Nearly all of this image is underexposed and dark, except for the very bright light bulb. I adjusted the ISO for my third trial. Here's a photo with an ISO of 25,600. It's pretty obvious that the entire image is overexposed, especially the lighter parts. My experiment showed that a very wide aperture or a very high ISO or a very slow shutter speed will increase the lighter frequencies of luminosity, while a very narrow aperture or a very low ISO and a very fast shutter speed will result in the opposite.